We've already learned that a long straight wire creates its own magnetic field, and we've also learned that a wire in a magnetic field can experience a magnetic force. So this video is going to put together those two ideas, saying that we have two parallel wires, each one carrying its own current. For the purpose of this video and our derivation, we're going to assume those two currents are each traveling upward, and let's say that the two wires have the same length and that the distance between the two wires is small in comparison to the length of the wires. So we know that each wire creates its own magnetic field, and we have previously learned that that magnetic field can be found using the equation B equals mu naught I over 2 pi r. A reminder in this equation that I is the current that is running through that wire, and R would be how far away we are trying to find the magnetic field from the wire. This gives us the magnitude of the magnetic field. We'll talk about direction in a little bit, but remember that we have a right hand rule that involves us pointing our thumb the direction of the current and curling our fingers around the wire to give the direction of the magnetic field. Now we also know that if we have a current carrying wire in an external magnetic field, it's going to feel a force. So for example, if we have wire 1 creating its own magnetic field, wire 2 would be in the magnetic field from wire 1, and so it would feel a magnetic force according to the equation IL cross B. Now in this particular instance, L is perpendicular to B, because remember L has the same direction as the direction of the current. And then again, as I mentioned, the magnetic field is curling around the wire. So if we were to focus on wire 1, the magnetic field to the right of wire 1 would be pointed inward into your screen or into your paper. We would represent that by X's. And so if if L is pointed upward and the magnetic field is pointed into the screen, then those two are perpendicular to each other. So we could find the magnitude of the magnetic force simply by multiplying the current times the length of the wire times the magnetic field strength. So if we wanted to look for the force on wire 1, then we could say that that magnetic force is equal to the current from wire 1 times the length times the expression for the magnetic field created by wire 2. And here I substituted D instead of R because D we call this the distance between those two wires. This would give us an expression to let us find the magnetic field on wire 1. We could do the exact same thing if we wanted to find the magnetic force on wire 2. However, if you think back to learning Newton's laws, you'd realize that the magnetic force on wire 2 has to have the same magnitude and opposite direction. Newton's third law tells us that. And so it would have that exact same expression for the magnitude of the force, but the direction would just be opposite. So to figure out that direction, let's use the right-hand rule. We'll start by figuring out the direction of the magnetic force on wire 1. So we know that that L vector points upward, so we'd point our thumb upward. We know that the magnetic field created by wire 2, where wire 1 is located, is going to be coming out. Because if I point my thumb upward and I wrap my fingers around that wire, just to the left of the wire, my fingers would be pointed out. So wire 1 is experiencing an outward magnetic field. So using the right-hand rule, my thumb points up, my first finger points out, and then my 3 fingers representing the force would be pointed to the right, showing that the magnetic force on wire 1 goes to the right like that. Now, we said Newton's third law tells us that the force on wire 2 has to have the same magnitude and be in the opposite direction. So wire 2 is going to feel a force to the left. You can verify that using the right-hand rule if you would like to. In the end, these two wires would attract each other. If I were to flip one of the currents, so in other words, if one of those currents was moving up, the other one was moving down, I would still end up with the exact same expression for the magnitude of the magnetic field, but my directions would end up being opposite. In other words, the two wires would repel. That's all there is to know about the force between two parallel current carrying wires.